I'm John Roberts. I work with Russ Tedrake, and I'll be talking about some of my thesis work on the control of fluid body systems via real-time particle image velocimetry. And so particle image velocimetry, or PIV, is a technique that has a long history in fluid dynamics to study fluid flows. We're going to look at sort of a new application actually use it to sense in real time for control loop, and I'll talk about it in some detail later in the talk. So fluid body systems, what do we mean? The sort of gold standard that we consider are birds, and in particular birds flying through a forest, sort of our favorite example of the kind of system we want to explore. So this is a bird of prey flying through a relatively dense forest. This is a camera actually attached to its back, and you can see the incredible roll rates and sort of agility. There's a really awesome part right here where it goes through a tree trunk, sort of incredible. So we would really like to be able to make an engineered system that can accomplish some form of control sort of at this level of performance, that we can fly through a forest. We have a big project with a number of collaborators trying to study how birds do it, trying to study vision to see how can you see that these trees are coming at you. And then we're sort of looking at, okay, if we know where the trees are, if we have this plane, how do we maneuver between them? How do we robustly actually sort of do this dramatic roll and go between this tree trunk? How do we hit that with some accuracy? So that is our goal, and that's the kind of problems we want to solve. A methodology for solving those for a relatively wide range of systems. So some motivation. There's been a reasonable amount of work on these kind of problems recently on trying to get these sort of agile fluid body systems. So this is Rick Corey's work from this lab, 2009. There's a catapult over here. It launches this plane out about 7 meters a second. It stalls. The angle of attack here actually goes beyond 90 degrees, and it lands on that target. And sort of by the end of the project, it could do that relatively robustly. And so when this actually executes this maneuver, you can see here is a little flow visualization. The stalled wing has this sort of dramatic periodic weight behind it. The flow is very complicated, difficult to represent. It's transient, and most of all, it is critical to the performance of the task. So if we want to slow down quickly enough, if we want to land on this wire, we can't sort of use the normal operating regime of a plane. We have to actually stall the wing, get enough drag to slow down that quickly. And so it's sort of critical that we take advantage of the full sort of rich domain of possible fluid dynamics when we're trying to execute these tasks. Outside the lab, this is an ETH and Raf DeAndrea's group. Here they just sort of have a little, I think I jumped the gun on that video, I guess. There. They have a little quad rotor. Yeah, a little quad rotor that they're trying to teach to follow trajectory. And they actually have a good model of this quad rotor. They have a lot of actuation, and it's still sort of a tricky thing to do, to try to figure out, okay, when we're moving relatively quickly, how do we actually follow this trajectory, which we know is executable with some level of accuracy. They keep missing, but through iteration, they can try to figure it out. Then Stanford, I'm sure a lot of you have seen this video before. They have a helicopter that can autonomously fly all sorts of dramatic maneuvers. They did it by something called apprenticeship learning, where they actually had an expert pilot fly the maneuvers a bunch of times, and they try to make the plane just do the same thing the pilot did and stabilize that trajectory. So these people are all sort of operating in a regime that's very difficult. And why is it difficult? It's because the fluid dynamics matter. It's because you can't sort of wrap that all up in some simple lift and drag coefficient and operate in a limited regime and assume things are linear, or sort of you're around a relatively small set of sort of fluid operating conditions and quasi-steady kind of behavior. The fluid dynamics are all very relevant to this. And fluid dynamics is hard for sort of these four big reasons. The global models are intractable. Navier-Stokes is a very hard sort of set of equations to get solutions for anything but the most trivial cases. They're nonlinear, so a lot of the control techniques that you may want to use are sort of ill-suited to highly nonlinear problems. It's tricky to use them in those cases. The underactuated dynamics, you saturate your inputs, you have a lot of degrees of freedom, you want to control this full 6-degree of freedom body, but you only have a couple inputs. And so trying to control the system with just a few inputs like that is hard, because you need to sort of coordinate the behavior of, sort of take advantage of the blending between one state and another state, and the sort of connection between your input and all the different states. So that is makes it sort of hard in general. And it's a big contrast from like an industrial robot where just a lot of power makes it easy. In this one, even with a lot of sort of input power, even with sort of strong control authority, it still can be tricky to control the system. And then a large and unobservable state. So if you are feeling gusts of wind, if you're in the wake of a body, interacting with that flow can be very disruptive to your control performance. You can't ignore it. So turbulence on an airplane is sort of maybe a minor version, because if you imagine a small UAV, the gusts of wind can be faster than the flight speed of the UAV, completely reverse the flow on the wing. Birds deal with these sort of issues where you can see a bird in a gust of wind can compensate for it somehow sort of elegantly. And so we want to figure out, okay, the state of the fluid is theoretically infinite, but in practice maybe there's a relatively high state representation that captures most of what you care about, but that is difficult to observe. It interacts with you in a complicated way, and it still has a relatively large sort of number of degrees of freedom. So we want to deal with these with sort of two different methodologies. The first one, well, all three of these, we're going to look at a approach with data-driven models. So effectively, instead of trying to build a model that captures the full domain of behavior, instead of trying to express sort of the full capability of the dynamics, we're going to look at collecting data just near the desired operating conditions. So we just want to sort of, if we're doing something that we care about, we want to collect data near the thing we care about and try to represent that in a simple way. And because what we're trying to represent is so limited, because it's only a small region of the state space, it is amenable even to relatively simple model classes. And we don't need a huge sort of first principles understanding. We can just collect data and build a model based on that is accurate for whatever system we're actually looking at. And then the fourth difficulty here, this is where we're going to use real-time PIV. So real-time PIV will allow us to actually observe this state. It's still large, it still interacts with us in a complicated way, but now at least we can get a handle on it, but we can actually see what's going on. And that will make the sort of the problem a lot more tractable. So to study these, we want a very simple system. Some system that has all the difficulties, have the same fundamental problems, but is easy to collect a lot of data on, easy to try things out on. We don't want to sort of have a lot of engineering difficulties and things breaking, like the planes. I'm sure when the people who work on the planes give their talk, they'll have awesome blooper videos. I've seen them. We want something that doesn't do that as often, 200 gallons a minute notwithstanding, so we can actually collect a lot of data and study the system. So our motivation starts with a very famous problem from controls called the cart pull. So the cart pull, this is where I need my prop. I don't have the bandwidth to balance something this short, but the cart pull is like balancing a ruler on your hand. Oh, maybe I do. So there we go. You can see I have too high gains. But so you can balance this. The thing is that you can't apply a torque directly. You can't just twist it. If you want to control it, you have to move your hand underneath and sort of control both your hand position and the angle of this pole at the same time. That's underactuation. You have one input and you have 2 degrees of freedom. So we want something like that. This captures both the nonlinearity, the sort of dynamics have trigonometric functions, and the underactuation. But we want to sort of deal with these other things too, the intractable global models and the large and unobservable state. And we want something more fundamentally fluid dynamical. So using this in motivation, we look at something called the hydrodynamic cart pull. So this looks a lot like that cart pull. You can imagine there's a little cartoon of a cart pull, but on top of an image of our actual hydrodynamic cart pull, which is a wing in a fluid flow, so in a water tunnel. So if you imagine, instead of balancing against gravity in the vertical plane, let's say you balance horizontally against a fluid flow. So you're like a weather vane. And the weather vane wants to point downstream because of weathercock stability. That's the stable configuration. But upstream, there's a sort of something like an unstable equilibrium pointing upstream, where a little perturbation will knock it and it will fall over. So we want that sort of geometry. But the dynamics of this are a lot more complicated because it's coupled to the fluid around it in a very subtle way. So the modeling is hard. And then, of course, if you have a vortex coming at you, if there's some, like if you interact with your own wake when you move dramatically, the unobservable fluid state becomes relevant. And that's something that you don't have to worry about in the normal cart pull. So this is a system that is convenient to relatively few degrees of freedom. We can collect data on very easily. We put it in water because water is sort of easier experimentally, but the relationship to those aerodynamic tasks is still there. It's sort of, the Reynolds number is not so far away from that glider task. And we want to sort of study this system. And so the rest of the talk will focus on experiments and sort of the control of this system, the hydrodynamic cart pull. So this is a big experimental system. We have, if you see these pictures, this is the flow direction, those arrows. And this over here is a big picture of the thing we built. This is about where the water shot out and hit Russ and I. So it just is a sort of standard water tunnel, pumps here. It dissipates the energy in this sort of settling tank, then comes in, goes through flow straightening, and goes through a little test section here. So this is what the test section looks like. It is, the flow comes in this direction again, and here's our little cart pull system. And so this is our experimental setup. This is a little cartoon that you'll be seeing throughout the talk, representing the same thing, your cart, your pole, the flow direction, and the 2 degrees of freedom that we care about. There's a lot of fluid degrees of freedom. We're not going to, we won't write down numbers for all those, I guess, but here's the position of the cart, here's the angle of the pole, and then our input u. So that's what we can do. We can apply sort of a force to this cart. So first we'll try to model this. The modeling task is difficult, but we can build sort of a quasi-steady model, assuming that's moving relatively slowly, assuming that we can sort of ignore the transient effects in the fluid and make a couple assumptions. So first, the cart is heavy and fully actuated. That's just saying that the fluid bouncing the pole around doesn't disrupt the location of the cart. The cart, we don't have to worry about the pole spinning around. It'll sort sort of ignore that. And that's reasonable because there's actually a reasonable amount of stiction and it is much more massive. So we can control the motion of the cart sort of at will, subject to saturations. The pole, however, that has sort of more subtle interactions with the fluid. So we'll model that as having flat plate lift and drag. We will say the damping, the angular damping is linear, which is an assumption we've tested and is reasonable. Of course, there's sort of higher order kind of damping too, but the linear damping is a reasonable model. And then we'll have an added mass term to incorporate the fact that as that pole swings, it's moving around water. And so using potential flow kind of ideas, we can calculate how much mass of the water should we include in the inertia of this pole. So you can write down these equations. They're nonlinear. They're a little bit hairy, but they, at the very least you can get them, and you can get a little simple nonlinear model for the cart pole. This model, though, here I've got a nice little animation, ignores the fluid state, and that is very important. It acts as if the fluid state is not relevant. So if you're interacting with the wake, if a vortex comes at you, it can't encapsulate that. And it's not like the parameters in the model have to change. It's actually, there's a whole set of other states that are relevant, that are sort of not present in the model. And so it's more limited than just we have the wrong mass. It is sort of, there's a large set of possible dynamics which cannot be incorporated in this model. So that you'll find the limitations of this. We'll actually run into them sort of not very long in the future of this talk. So here's you'll be seeing a bunch of pictures like this, so I figured I'll make it explicit. Here's the pole. That's what it looks like. And also, everyone always thinks that this means that the water tunnel's really dirty. This is not dirt. These are seeding particles for PIV, so I'll talk about them. But I keep the water tunnel clean. That's just, that happens. So forgive me for it. And then this is the cart. So this is what we can move back and forth. And then this here is a perturbation wing we'll use in some later experiments, but for now you can ignore it. So concentrate on the pole and the cart. The water flows in that direction. So here we have the basic task you could imagine is wanting to balance it at the upright. So here it is balancing. You can see it's moving back and forth. That little green dot means that it's on. At some point I'll hit the E stop. That's when the little green dot will turn red, and you will see that without sort of the control on, it falls over very quickly. So that's the kind of geometry of the system. I want it to fall over like that. So how do we actually get it to balance? Well, we only can measure the position of the cart and the angle of the pole. So we have that model, so we can use that model to build a dynamic observer that will give us the velocity, so sort of the full internal state of that cart pole. Still neglecting the fluid, but will sort of give us a relatively up-to-date idea of the behavior of the cart instantaneously with relatively little latency compared to finite differences or something, for example. Using the model, the nonlinear model, and linearizing at the upright configuration, we can get a linear model which is amenable to LQR design. That's a standard optimal control kind of design technique. And we get a PD controller just on the estimated state, and that's enough to balance, as you saw in that previous video. That sort of simple control technique with linearization and the quasi-steady modeling will work in that configuration. How robust is this controller? So you can hit it with your hand and it will stand up. It's sort of robust to that. But the more interesting question of robustness is when it's in a sort of complicated fluid regime. So here we'll put the cart pole behind a flat plate, so sort of a bluff body that we're just holding in the flow. That'll shed a vortex street, as you see, sort of counter-rating vortices in a drag wake, and they'll hit the pole and bounce it around. And can the sort of balancing controller, which doesn't know about this kind of structure, can it respond and sort of balance even in that configuration? So here's a little video. Once again, the control is on, and we'll turn it off and show how it falls over, but that's just holding a little plate upstream. At some point, you will see it fall over there. So without the control, it quickly falls over. So these tests are interesting, but what we really want is we want to have it actually accomplish more than just stabilizing. We want it to be able to execute a maneuver. And so here we'll look at sort of a very basic maneuver called tracking a step. And the goal is not really to follow a specific step trajectory. It's to go from one position to another position in the cart while keeping the pole upright as quickly as possible, or within actually a specified time frame at 1.5 seconds is what I used. And so this you can imagine is analogous to a plane executing a quick maneuver to change altitude. For example, if it was running at a tree branch and you want to sort of jump up and point the same direction, but be at a slightly different altitude, this could be an analogous kind of task. So what's cool about this is because of the underactuation, you can't just drive straight to where you want to be. You actually have to take into account the sort of coupling between these degrees of freedom. So here we can bounce the cart backwards, sort of in the direction you don't want to go. The pole starts falling over, and then because it's falling over, you can stabilize the pole by moving to where you do want to go. And that's sort of a characteristic of the underactuated system, and also in some way you can say this is non-minimum phase for some input-output relationship, and it's characteristic of that as well. So we want to execute that kind of maneuver. The simplest thing you could try to do is just use our balancing controller. So be bouncing around one point, and then suddenly just sort of tell it, oh wait, no, you're at the wrong state. You actually want to be 4 centimeters somewhere else. And it'll compensate for that the same way it would compensate for any other error. So you just sort of have your desired state switch by 4 centimeters all at once. Here we'll do that. This little dot now shows the step turning on or that there. So you see it moves pretty slowly. You can see it executing, but it's not very quick. That's just following the step through the balancing control. Here's several plots of it. You can see it takes 4 or 5 seconds to climb up 4 centimeters. It's not very satisfying. We can get there. It is stable, but we want higher performance. We want to sort of execute this task much more quickly than this. And so there is a way to do this. We have a model of the system. We have parameters of the task, so we know we want to sort of move 4 centimeters. We know sort of how the system behaves. We can put these into a trajectory optimizer, and we can actually generate a feed-forward controller. So a controller which isn't just responding to it like an error as a feedback controller, but actually tells it where to go, tells it the direction to move in, and has an understanding of the coupling between the degrees of freedom. And this should allow us to execute with sort of higher performance. Whereas the feedback controller, you can turn the gains up, but at some point it actually destabilizes, and I sort of push them up as much as possible. So just making the feedback controller sort of higher gain is not a way of solving this problem, but this feed-forward one actually is. So we can design this feed-forward trajectory, execute it. Once again, you'll see the step turn on. This one's much more obvious in the video, though. It'll suddenly turn on, and you'll see it kick there pretty quickly. So that's nice, but it overshoots heavily, if you see that. It's sort of, maybe I'll play it one more time. It overshoots the desired point. So we want to do better than that. And that overshoot is not because the trajectory said you have to overshoot to meet these constraints. It's because of the limitations of the model. It's because the model doesn't know the full details of what's going on. It's because it's moving quickly enough that those complex fluid dynamics, the interaction with its own wake, for example, are becoming relevant. And the quasi-steady model can't capture that anymore. So we want to figure out a way, without having to necessarily build a richer, fully complex model that can deal with the wake, a way of tracking this step more accurately. So we'll follow a data-driven control kind of approach. So the idea of this approach, or maybe I'll stay on this slide for a second. The idea of this approach is that we're tracking a step that's not so far from what we want, but it overshoots, not sort of exactly meeting our requirements. But we're getting data of the system near sort of the domain we care about. So instead of trying to build a bigger model that captures everything, really all we need is we just need to use that data to get an understanding of the system locally, near a step, effectively near a 4 centimeter step. We can build an idea of how the system behaves in that domain. Then using that model of that local understanding, we can be like, okay, here's how to make it a little bit better. Here's how to reduce the overshoot a bit. Here's to finish up with a little bit less velocity. Here's how to meet these constraints in a locally sort of better way, without making a huge update where you leave that domain. So you sort of stay within your local data's relevance and slowly climb your way towards better and better performance. So this sort of iteration is a little cartoon algorithm now. We use the trajectory optimization and that initial quasi-steady model to design a feasible, faster rising trajectory that does a reasonable thing, but is not exactly sort of what we want. It doesn't meet all our constraints. Sorry. We stabilize the trajectory with a time-varying linear controller. So the same sort of LQR approach we used previously, we'll use in this one. But because the system is changing significantly, we'll actually make it a function of time, not just a fixed control gain. This will deal with the fact that the trajectory is not ideal. It's not exactly so the system's not perfectly correct. And this will give us some robustness to the errors in our model. And also make sure that we sort of do something reasonable and don't just run an open loop trajectory that does something irresponsible. So we collect all these trajectories, and around them we can fit a time-varying model that captures the behavior of the system near the captured data, not elsewhere, but just near that data. And because that's sort of a relatively small domain, even a simple linear model is enough to represent those dynamics. Then within that model, find a corrective trajectory. So for example, something that reduces overshoot without increasing overshoot in another degree of freedom, without sort of having too high velocities at the end, sort of respects the requirements of the system, but locally improves it. And we iterate this, doing several small steps, stacking them on top of each other, until we converge to something that meets the requirements we have for the system, that sort of does well enough. So here, after doing this procedure several times, after doing about 7 iterations of the procedure, collecting data, building a model, and then updating, we get a new trajectory. And this one, I think, is pretty clear just when you see the video. When it turns on, it hits the sort of target and overshoots a lot less, has less ringing. So it looks a lot nicer, right? So if you actually plot these, you do a bunch of them, you average them. These are the average of those 3 different cases I showed you. The balancing controller in blue, that's just the LQR controller, and you see it rises very slowly. The red is the initial feed-forward one I showed you that had overshoot and ringing, and then the green is the final one. So you see it sort of meets these requirements a lot better, has a lot better performance. So now I think the most exciting part of the talk maybe is how do we deal now with fluid perturbations? if we previously were looking at doing maybe a quick agile maneuver, but we're not worried about a gust of wind, we're not worried about interacting with the wake, we're sort of just worrying about having the system do something in a free stream. So now let's say we actually have a perturbation to the system. So now you actually have to worry about this wing. And this wing is just called the perturbation wing. We can control it and kick it and send a vortex off downstream. So it'll vect downstream and hit the card pole. We don't let the card pole sort of know what we've done though. So we can generate it to sort of run these tests, but the card pole is just getting hit as if it was unaware of the generation of that vortex. And it has to sort of deal with that either as a perturbation, or later on we'll try to sense it and respond to it sort of with foreknowledge of it coming. So here's just a little video of the LQR balancing controller getting hit. So you see a big deviation. Gets knocked pretty far from where it wants to be. Show another one. So what we want to be able to do is get hit by the same kind of vortex, but have smaller deviation, or do better by some measure, and different measures could be used. So how do we pursue this? I'll show a little cartoon. We'll be seeing some of these cartoons through the rest of the talk, so there's a good way to explain it. That's the pole you see down there. That's the perturbation wing that we're kicking. Here we're actually playing back a real trajectory. So this is actually data. It's bouncing there behind the pole. The pole goes, has a little cartoon of the vortex, and knocks it over to the side. So we want to be able to deal with that. I don't have to play it again, I guess. So it's bouncing and it works well, but this is the situation where we have a large and unobservable state. So here we're really interacting with with sort of the fluid and large fluid perturbations. We don't have a good model of how this vortex interacts with our pole, so we need to figure out some way to, when getting hit by this vortex, compensate for it in an intelligent way without having a good model. And in this case here, we don't even know that it's going to hit us. So if PIV gives us sort of foreknowledge, and we know that it's going to come to us, that's still not easy because we still don't know how to take advantage of that foreknowledge to reduce the size of the disturbance, or reduce the, sort of the total deviation experience. And that'll be the kind of question we're looking at. So PIV is the way we're going to give ourselves this foreknowledge. And I'll try to describe the algorithm here in some detail so that you'll have an idea of how it gives us this information. So the PIV setup, here's our test section again. Here's a little schematic. That's the pole. That's the perturbation wing again. Now imagine we have a laser. We put it through a cylindrical lens, and we get a little laser sheet. That laser sheet illuminates sort of a 2D slice of our test section. We put in, oh, you can't see those too well, those little dots. We put in a bunch of little polystyrene beads. The laser illuminates those beads, and we put in a camera that can view sort of in between the pole and the perturbation wing. So this camera actually can take pictures of the flow, take a picture of those little illuminated beads in between the pole and the wing, and sort of see the flow in the future. See what's going to hit the perturbation wing, see what's going to hit the card pole system sort of maybe a half second in the future. Here's just it running. This is what it looks like when the laser's on, just on the test section. And these are the kind of pictures you get. So I'll show the little video. Those are little beads you see there, just moving the wing, and you see a nice little vortex shed off the tip of that wing. And so from your eye, it's clear that you'd expect the information to track this vortex is there. You can clearly see, by looking at it, that there is the information you want present. The question is, how do you extract that automatically? How do you get your computer to sort of find that vortex? So here's just two images from that video, 2 frames. You see just a little bit between them, they only morph a bit. Those particles just look like they're shifting a bit, and that's what you're seeing. So if we can say, okay, if we want to say the block of particles in the first image matches up with which block of particles in the second image, how do we sort of correlate these two images and find where the pixels in the first one went in the second one, which will give us where the fluid went? So we can take that block and compare it to a bunch of other regions, sort of a bunch of other blocks of pixels. We can take these, sort of look at them closely, and measure the distance between them. So this looks ugly, but it's actually just the error correlation. It's sort of one of the ways of measuring distance in pixel space. So you have 2 blocks of pixels. You want to see how similar those blocks of pixels are. Where those are very similar, this error correlation will be small, and the match is good, and that's where you sort of think the fluid went. Where it's large, it's unlikely that those particles went there, and that's sort of where you don't think the fluid went. So if we do this, we get a vector field sort of all across the image. I'll zoom in a bit. You can see it is capturing that vortex. We can see the sort of shape we want to find. We want to see this sort of little spiraling shape. But we also have a bunch of these bad vectors. We have missing vectors. There's some outlier rejection that I do, so that's why some of these are just completely missing, but also there's some that just don't look right. And so we want to find a way to robustly identify this vortex without doing something like computing the curl of the vector field, which would be very noisy. So we're going to look at actually using, so PIV is a sort of technique that's been used for, well, since the mid-'80s. It's a good review paper. Also, for most of the sort of history of it, the limitation has been how long it takes to compute. So you take a bunch of data, sort of when the experiment's going on, you store it, and then you process it offline. And people have tried to make that faster, even just for the offline processing. More recently, as computers are getting faster and faster, it's reasonable to actually do these calculations in real time. So sort of instead of after the experiment's complete, you can take that vector field, do the calculations, get the vector field while that sort of flow is still present, and give that to your controller. And so people have been interested in this for the past 6 years or so, maybe longer. And through an FPGA implementation have done the sort of calculations fast enough that you can imagine putting in a loop. Where the stuff I use on a GPU, we have a collaborator who's working on sort of GPU implementations as well. But really the computing power is there now. And what we're trying to do is, for the first time, really taking this information and using it in a control loop. Where previously people have got these calculations up to the speed you need, they haven't used them in a way to actually improve control performance. And that's what we're sort of doing. That's what we're adding to these technologies. So to find that vortex, we will try to search for, we know the shape of it that we want. We want to find that sort of spinny shape, but what really does that shape mean in a more detailed sense? Well, in fluid dynamics, there's a model of a vortex called a Rankine vortex, which has this rigidly rotating core here, which sort of just spins around. That's where viscosity is dominant. And farther away, we have this shape, which is a sort of irrotational vortex in a potential flow, and then you blend them together. And so what we want to find is we want to track on that sort of farther out irrotational vortex component. We want to look for the shape of an irrotational vortex in the flow. So just seeing, is this model a reasonable sort of representation of what we're seeing? Here's a little simulated video of a Rankine vortex moving through a simulated particle field. You can see qualitatively that is, I think that is a very reasonable sort of flow field. So I think that looks about like what you see in the real data, and so we're going to look for something of that shape. Here's the example of actual fit. So you pick a candidate center, you compute the tangential velocity as a function of radius. That's what this plot is showing. And the Rankine vortex tells you what you expect that function to be, how you expect that to behave as a function of radius. So the Rankine model is this black one. That is sort of it's a 1 over radius kind of shape. A good fit is like the red one. That matches that shape pretty well. A bad fit is the blue one. That is sort of a bad candidate center where the tangential velocity is not at all what you expect it to be. That means it's unlikely that that is actually the center of your vortex. You do a bunch of these over your image, and you get this sort of shape with a hump in it. The middle of that hump is where you want to be looking for your vortex. Sort of at some point it limits down to, some minimal fit, and depending, so I think some of that is correlating on the wing. That's why it looks so bad. But you want to find sort of the peak center of that. So if you zoom in on the center and you have an idea of where that center should be, just because the vortex, if you have a guess of where the vortex is, you can sort of even zoom in and not do all those calculations. But you have a nice actually shape here. This is sort of a nice little bivariate kind of quadratic shape. You can fit this in least square. You can use least squares to fit that bivariate polynomial very computationally quickly, so you can do that in real time, and then in closed form get the peak of that, and that'll give you an idea where the center is. So that little red dot is the sort of estimate center that we get from doing this fit on the vector field. If we do a bunch of those, it bounces around a bit, but it does a reasonably good job of following the center. So I think that the results from these measurements are pretty good, but clearly we don't expect the real vortex to have that sort of high frequency noise. But because it's such high frequency noise, it's reasonable for us to try to filter it out. So because we assume the vortex has some momentum, it's maybe some second order integrator kind of dynamics on the center of that vortex, we get these green measurements sort of saying it bounces all around. And we get that red filtered one by doing the same kind of filtering we used previously. So that same structure of observer that just says, okay, it should have momentum. If you have this sort of high frequency noise that's probably not physical, just average it out and track the center. So we get pretty good tracking using that sort of filtered vortex center. Now, we're going to reject these. So now that we can see these structured in the flow, now we can actually identify things in the fluid, which I can place. We want to use it to reject these fluid perturbations. So here's that same video again of the balancing controller getting hit by a vortex generated by the perturbation wing. But now we're going to see, okay, if we can tell when those vortices are going to come and hit us, what sort of controller can we design that will reduce the deviation we experience when we're interacting with that wing? So here we collect a bunch of data again. We have a bunch of trajectories of the system getting hit by vortices. We again fit a local linear model around the measured data, and we say, okay, how do we compensate for the perturbation in this model? How do we design a controller which, when it sees that vortex ahead of you, starts executing a controller that will minimize this deviation, using the sort of local understanding of how that vortex affects us? If we do that design, we now have our sort of full control system in place. We have a camera that's observing the flow. We have the actual test section, which is our experiment. We have one computer just doing the observer control, like running the observer, running the controller, interpreting what to do. We have another controller dedicated completely to processing those images and talking to the camera. And that has a GPU dedicated to doing these calculations sort of in parallel as fast as possible. So we have sort of two computers, one looking at the flow and telling our control computer, this is what's coming at you. The control computer then has an observer and runs the controller and takes the information from PIV and says, okay, we're about to be hit by a vortex. Let's use some compensation. So here, using the same methodology that we used in the first half to track the step, we now design a sort of, through iteration, a compensation trajectory that will minimize the deviation. So this is trying to minimize the pole angle displacement. So not how far the cart moves, but how far the pole goes from the upright. So designing a sort of compensation trajectory to minimize the effect of that, we have, you see the cart moves, but look at the violence of sort of that kick to the side. So we'll see another vortex come by. And the pole has a relatively small deviation because the cart sort of runs underneath it. Show one more. So now, here's a little cartoon, also playing back real data. The lighter one is PIV, the darker one is LQR. This is, again, minimizing pole angle displacement. So this is just a little cartoon. You'll see the perturbation wing move. Kicks off a vortex. The PIV one sees it coming and is able to sort of jump out of the way a bit and run through the center of the vortex, and has a much smaller deviation in its angle. I'll play that one more time. I think that's pretty cool. Here we go. They're just balancing there, complacently not knowing anything's coming. Now the PIV one knows. You see how it sort of jerks forward and moves and jumps around and keeps its pole from falling too far to the side. I think that's pretty cool. Here's a little plot showing the PIV and the LQR traces. So this is averaged over a bunch of trajectories. The PIV clearly on average has a much smaller deviation, and this is in theta. Now you may be wondering, is it important that we use the PIV, or is it really just that feed-forward control is what's necessary? It's sort of just designing that compensation trajectory is what gave us the advantage. Well, here's designing a compensation trajectory that we tell about the perturbation half a second later than PIV, which is about the time that the vortex really starts interacting with your pole. So if you were just to identify it locally, if you were to have local sensing that told you this perturbation was going to come, you would know about half a second later, how can you design a trajectory that compensates? And you see in that green one, it doesn't do significantly better than LQR. So you need that sort of early information. You need to be able to see in the future of the flow. Here's the same kind of plot. This is plus or minus 1 standard deviation. So it just shows that even taking into account the variance of the system, you have a much improved performance using PIV than you do with LQR. Now we have, let's say we want to follow that same procedure. We'll follow this procedure for a different objective. We're going to try to minimize the cart displacement. So it's okay in some sense if the pole has a large deviation. We don't want it to fall over, but we don't want the cart to move too far away from 0. So here again, the same color scheme. Lighter is PIV, darker is LQR. Vortex comes away. You see PIV sort of like runs out of the way, lets the vortex sort of suck the pole back towards 0, and then balances it with a relatively small deviation. So I'll play that one more time. So there they are, balancing. The vortex is shed from the perturbation wing. See PIV sort of jumps out of the way. The vortex pulls the pole back upright, and you sort of jump back to the center. You have a much smaller deviation. So here again is some statistics on that, a histogram comparing the PIV maximum deviation after perturbation to the maximum deviation from LQR after perturbation. So you can see that the sort of average deviation you get from PIV is significantly less than LQR. We can again look at giving the information a bit later, half-second delay. This does better than LQR, but it doesn't do as well as PIV. So it's sort of what you expect. Doing that optimization does help you a bit, but it doesn't give you the same sort of performance you can get by being able to see into the future of the flow. So these results, sort of tracking the center of that vortex, getting the sort of information of the vortex coming at you during the perturbation experiments, we were able to do, well, we do it with 400 vectors. And we can get those about 33 milliseconds. So 30 frames a second is the kind of rate that we can do this processing. So when we say a vector, we mean like that picture I showed you with all those little red vectors. That's we're computing 400 of those and using those to identify these shapes. If we could get more vectors, though, we could perhaps identify sort of finer grained structures in the flow, something more subtle than just this vortex. Or if we could get the same number of vectors, but in less time, we could look at faster flows. If we could sort of look at a faster camera and process it, we could look at maybe 100 frames a second and get sort of dynamics of a higher Reynolds number. So this is just showing that the GPU has bought us a lot. This is the time in milliseconds versus number of vectors. So again, for about 400, we're at about 33 milliseconds. So up to even 1,000, we're at about 15 image pairs a second. So we have pretty good processing. And then at the next one, the scale over here is the ratio of the serial computation to the GPU computation. And again, take this number with a bit of a grain of salt because it's the same implementation. It hasn't been like heavily optimized for either hardware. So I think both of those things can be improved. But using this sort of same kind of methodology, you get at high numbers of vectors, you get like a 80 times improvement in the speed by doing it on the GPU, which is sort of what you expect. As the number of vectors gets bigger, the advantage of that parallelization gets bigger, and you start seeing a huge speed up. Right now, however, our bottleneck for our system is really getting the data from the camera. Is that pulling the images from the camera so we can process them on the GPU is our biggest limitation. But we have a collaborator who is looking at doing an FPGA implementation, which you can imagine actually putting on the camera, so sort of before you pull the images off. If that could process and actually get the vector field on the camera and just send the vector field data over, the sort of bandwidth of that connection would no longer be the limitation. And at this point, you really want to be able to calculate as quickly as possible, because without we can have cameras take sort of video very quickly, and if we could process those very quickly on board and send the vector field, we could really look at quite high-speed flows. We could look at sort of very subtle kind of effects. So I think an interesting research direction is how can we look at fewer vectors and get the same sort of accuracy of performance? How can we recognize the center of a vortex with fewer measurements? If we can do that, we can look at a higher speed flow again by just sort of cutting down the computation without accepting inferior performance. And I think a good framework for looking at this is compressed sensing. So with compressed sensing, we can try to sort of extract the same sort of low order information with fewer measurements. And by fewer measurements, I mean generating fewer vectors. And so if you can sort of just generate a small subset of those vectors you were looking at, there's less calculations necessary, and you can get perhaps the same sort of vector field information with many fewer vectors in your field. So how do you do this? It's sort of the formulation of the problem is a L1 regularized least squares. So you have a least squares problem, but instead of just sort of finding the x that minimizes this squared error, you also penalize the L1 norm, so just the absolute value of x. And so in this way, if you think of it in the context of our center tracking, let's say when we look at these different radii, how do you interpret the weighting of that radii? If you fit really well at small radii, but you don't fit well at like radii far away, are those equally bad? Are those equally informative? It's not obvious, right? This is an optimization procedure that can give you some clue as to that. So if you know what centers you want to get, or you know what fits you want, you know sort of this is the answer I want, but let's choose how to weight the radii based on this optimization. So sort of the x now here is how much weight do I put on sort of close radii, medium radii, all the way out. Sort of 18 different groups is what I did. The result then, by putting in this L1 norm, is you're sort of pushing for sparsity. It's not exactly sparsity. Encoding exactly sparsity is actually an NP-hard problem, so something you can't conveniently do. But this becomes a convex optimization program, and so if you take a bunch of data, you can solve it relatively quickly, not online, so it's not like we're doing this while running the experiment. But if you collect sort of vortex perturbation data and you do this optimization, you can now fit the vortex center based on just a subset of that sort of true offline computation you did. So you do a bunch of computation offline, get the sort of benchmark answer, try to figure out, is there a way I can produce that with less calculations? If you do that, you do get a much sparser representation. And here you have, on the left, this is the sort of rough center track. This is actually just the measurements of, the green is the dense one, the one I previously showed you. Blue is from the sparse process. So you see those measurements are a little bit different, but largely the same. And on the right, we have the filtered one, where you put them both through the same kind of observer. And in this one, they're a little bit of drift, but a drift of only a few pixels. And so really by doing 60% fewer correlations, so a lot less sort of work is necessary on the GPU, we get tracking that's similarly performing. So if you can deal with this few pixels error from your benchmark possibly, you can maybe speed up by a factor of over 2. And that's sort of the goal of this kind of framework. So to go through the, it's about time, to go through the summary and contributions of the work. So this is the first complete implementation of real-time PIV in a control loop. So people have real-time PIV that's running sort of the necessary rates, but not using it actually to control a real system. And so here we actually have an experimental system using real-time PIV information to improve the performance of its control. And we've also been the first people to demonstrate, I mean, I guess this is, you'd have to be the first for this one, if you're the first for the second one, the first demonstration that this PIV information is not just something you're doing to study the system, but actually something that makes you better at controlling it. So the information is actually useful for improving your performance. And that's sort of, I think, not a surprising thing. You expect by being able to see the future of the flow, you should do better. But I think it's cool that we've demonstrated that this information really is useful, and that knowing about the perturbation even a little bit later doesn't give you sort of nearly as high performance as knowing about it, sort of upstream when the PIV senses it. Then demonstrating this data-driven control approach with only a little bit of prior knowledge. So people have been using these sort of data-driven mechanisms in various forms to study those systems I showed earlier on, where, for example, that helicopter that was flying, they did update the model based on data, but they sort of had an initial feasible trajectory that someone had given them by being an expert pilot. And then similarly, other people maybe have a very good first principles model and iterate a bit, but have a good sort of starting point. Here we've actually had sort of we use that quasi-steady model to get us close, but in the sort of iteration and learning procedure, it was all just purely from data. And we were able to have very few assumptions, have a very weakly actuated system where the underactuation was sort of a critical component of its behavior, and still show that the optimization can work even when the dynamics are as complicated as an underactuated sort of cart pole getting hit by a vortex. I think that's cool, that really this sort of design approach and this data-driven approach works quite robustly. The same sort of approach works robustly across these different configurations for actually a very complex dynamical system. And then we showed that compressed sensing, that sort of methodology, can give you big gains in the computational burden for doing this. So if real-time PIV is bottlenecked by the actual calculations, there's, I think, a lot of really exciting directions to go of looking at, for different configurations, what sort of model do you have, how do you sort of formulate the problem for the sparsification, and how much sparse or how many fewer vectors can you look at, still get similar performance in your estimates. And really, as you get more and more understanding of the fluid flow, you can get sort of equally good estimates of the fluid state while doing only relatively few correlations. And that's sort of another, I think, exciting direction, is trying to pursue how much sort of better you can do even in the compressed sensing I showed here. And then so what's the future direction? I think that there's really a lot of exciting future directions. Sort of imagine a bird that can see the fluid upstream, the fluid sort of in front of the bird. Imagine if it could compensate for the disturbances and gusts of wind before it felt them. The sort of study of that kind of problem could really give a handle on the subtleties of interacting between a gust or a fluid sort of disturbance and the body in flight. Because really, if you're looking at just local measurements and trying to compensate in that space, you're very limited by what you can see. If you can control in this sort of fully observable case, there's a lot of good science, I think, that you can study as to how do you compensate for sort of this reversal or this sort of this gust sort of reversing the flow on your wing, for example. And just studying how do you do that and sort of what can you do? How limited are you by the local sensing compared to if you knew what was happening? There's a lot of interesting questions there. Then, in a sort of applications-focused way, you can use these PIV experiments to sort of train a local sensing suite. So maybe you can't go fly actually through the forest with PIV in front of you. But if you can design your model system in the lab and you can study it using PIV, design a benchmark control task, and then put on pressure taps, put on anemometers, put on the usual kind of sensors, you sort of have a benchmark right answer, the sort of like best level of performance and an easier control design task, because you actually can observe the full state. So you're solving the fully observable problem. Then if you want to try to figure out, okay, how well can I do getting rid of PIV and just looking at these pressure sensors, you sort of have a handle on that. And that's sort of why we say it can be scaffolding for that kind of problem. If you design it in the PIV context and you study it sort of in this fully observable space, the control design is easier, you have a good idea of what performance is possible, and you can say, okay, how much do I sacrifice by putting on these pressure taps or only getting these velocity measurements? And also just saying, okay, this is the right thing to do. Is there any way to extract that from my local measurements where it could be hard to even sort of know what I'm looking for in the measurements without having that design? Then finally, leverage the richer fluid models and generalize to new flows. So there's a lot of, I think, there's a lot of possible directions in which you can use this really in a laboratory, where if you're a fluid dynamicist and you're studying some system, if you're studying a fish swimming or a bird flying, and you want to get a handle on sort of the dynamics of that system and how it interacts with the flow, just measuring the kinematics of a biological body, for example, and playing them back is not necessarily exactly what you want, because there's some subtle interaction going on that you may not be sort of optimizing. You may not actually be sort of looking at exactly the right thing. So if you can actually design these controllers, design sort of a compensation controller for a gust of wind in this sort of actual dynamical control sense, then you'll sort of be looking at it in the right way. You'll be looking at the sort of subtle dynamical interaction between the body you're controlling and the flow, as opposed to maybe doing a sort of a study on a bird and then trying to make your robot bird do the same thing. You actually can make your robot bird do the right thing in sort of the right context, which is actually this dynamical interaction with the fluid around it. So I'd like to, of course, thank a lot of people for all of this. In particular, my advisor, Russ, who's been a great advisor, I guess, from the start of it. I think he was sort of always there when I started out, and it gave me sort of enough free rein at the end that I could spray myself with water without anyone knowing. So that was good. Yeah, almost no one knowing, as long as I had brought an extra shirt to lab. I mean, he's been, I think, a great mentor and a friend, and I really appreciate the opportunities. I'd like to thank my committee. They've all, I think, the meetings I've had and sort of gaining the direction of what to do and what experiments and what are the interesting problems to look at, I think I owe a lot to them. I think that they gave a lot of good perspectives on just what was the right way to sort of look as I was getting these results and sort of thinking of the next thing to look at. And in particular, I've got to give a shout out to Professor Hart for giving me a pulsed laser when I was very much in need. That was a desperate time for me, but it worked out. And then, of course, all my lab mates and collaborators. I have undergrads who worked with me, Jacob Steinert, Sambaran Sharma, Elena Glassman. There. So then Steve Poole was a sort of lab tech who helped me build that water tunnel, and I owe a lot to him. He was great. And then a sort of bunch of people in my lab who've helped either sort of specifically with running experiments and sort of with higher level questions of just research. And I think I've learned a lot about them on many fronts, both sort of related directly to my research and just generally a better understanding of things in general. So I'd like to thank all of them too. And if you have any questions, I would love to take them.